Good morning, I'm Giovanni Lugaresi from Politecnico di Milano, and today I will present you the joint work with my supervisor Andrea Matta, which is titled Generation and Tuning of Discrete Event Simulation Models for Manufacturing Applications. This work starts with the realization that modern manufacturing systems are fairly complex systems which suffer from the pressure from market demand and cost reductions and high cadency of production. This means that failures can have a big impact on the production, and online support tools are needed for production planning and control and for taking decisions in the short term. The recent Industry 4.0 revolution can also help because it provided us with technologies which are able to collect and store information which are very affordable. So we might design online support tools to take decisions in the short term. We might use simulation models as online support tools. In this slide, we can see the main problem that we might encounter. We have a manufacturing system on the bottom and a simulation model on the top. We see that along time, the manufacturing system might change and the simulation model does not follow the changes of the system. For example, we might add a station or we might change the part routing along the system. In this case, the simulation model, if it is built with traditional technique, does not follow the changes in the system. Hence, we cannot use it to take online decisions, to take decisions in the short term. But if we are able to use the data coming from the real system to design a simulation model, then we might infer that we can generate a model at any time and the model is properly aligned with the real system. So we can design digital models and we can use them to act on the system. The literature can help us because in the recent years we have had several contributions which are building simulation models starting from the event logs. This is also thanks to the development of process mining techniques, which are basically aimed at generating models starting from the data. However, the contributions in the generation of discrete event simulation models for manufacturing systems are relatively scarce. And there is not a strong focus in the representation of the resources, which are very important in manufacturing system, and there is not a clear link between the performance of the generated models with the ones of the real systems. At the same time, the model generation techniques based on process mining usually tend to generate models which are too accurate with respect to the intended purpose. So there is also the problem that the models might be not so easy to use in production. So I will give you a short overview of the problem that we want to address in this work. We have a manufacturing system starting with the 3 stations. Each station has 2 sensors, and as we said, we can have data coming from the system which are collected in an event log. The event log might look in this way. We can use an event log with 3 columns, a timestamp, a part ID, and an activity ID. So basically each row will tell us at what time a part has performed a certain activity. At the same time, we can notice that the model generation will design models which are basically representing activities as nodes, and each activity is represented by a node, and the arcs are representing the precedence among activities. At the same time, we notice that the generated model of the system is too accurate because we know that in this system we have 3 stations, and typically we would like to have a model that looks like this because we know there are 3 stations and we usually are accustomed to use these models, and the performance of the model is more representative of the real system. So in this work, I'm going to show the model generation and model tuning. The model generation, as we said, starts from an event log. The event log records the activities that are done by all the parts in the system. From the event log, we can generate traces. Traces collect all the activities that are done by each part. And from the traces, we can derive the activity relationships. So we can, for example, say that if station 2 follows station 1 in any trace, then it means that we can generate a model in which we have two nodes, so one for station 1 and one for station 2, and an arc that connects these two nodes, representing the precedence between those two activities. Then we can add parameters which represent system properties. For example, between two stations, we typically have a buffer in which part can wait for the next station to be available. Then we can infer that from the event log, we can see parts were accumulating between those two stations. So we can infer the buffer capacity as the maximum number of parts that we have observed waiting between those two stations. And we can add this property to the arc connecting the nodes 1 and 2. Then, as I said, we need a way to tune the model towards a proper level of detail. This means that we can aggregate nodes in clusters representing similar activities, or we might also exclude nodes and arcs from the representation, simply removing them from the graph model. But how do we take this decision? We have designed scores which represent how well a model represents a system property. For example, we can design a score which tells us how the closed events are represented in the model. By closed events, I mean the events that happen between timestamps that are very close in time. So, for example, in this slide, you see three different options to aggregate nodes. We have a 3-node initial model, and we want to go toward a 2-node model. So among the several options, we see that the central option is to aggregate nodes 2 and 3, and among the others, the number of close events between those two nodes is the highest. So we can say that this is the best option, and we can go on and aggregate those two nodes. In the same way, we have designed other scores based on other properties, for example, the frequency, capacity, or the presence of loops, for example. And if you're interested, I could give you more details. Then we have designed a local search algorithm, which starts from the initial model and goes towards the model with the desired size. Basically, this is based on the possibility to generate neighbors of a model. We start from the initial model and we generate a set of neighbors. Then we select the best neighbor and we go on. But how do we generate neighbors? We can generate them with two main actions, the reduction and the aggregation. In both cases, if we remove elements, we can say that the properties of those elements will be inherited by the added element of the new model. So now we are able to generate models with the accurate size. In this slide, I show the possibility to convert the obtained models in Petri Net models and event relationship graphs. So we have taken the log of an MM1 cube, and we can see that these are three different alternative representations. We have a process model, a graph model, a Petri Net model, and an event relationship graph, which can be obtained by converting the Petri Net model using a method which is available in the literature. In this other example, I show how this model tuning behaves with a flow line. We have a flow line of 6 stations, and we have a flow split in the last station, between the last station and a quality station. And we can see that depending on the ratio of parts going to the quality station, different stations get aggregated. So if we have less parts going to the quality station is aggregated to station 5. We can also ask for a more reduced model, and we can also ask, the simplest model is a 2-node model, in which we can see that the result is that all the activities are aggregated in clusters. And we have the result is a 2-node model. Then in the last month, we went on with the work, and we also performed the validation. The validation means that we take the generated model, starting from a complexity threshold, which is the dimension of the model, and we can see what are the performance obtained by those models. And we can compare the performance with the performance of the real system. In this graph, for example, you see the comparison of the throughput. The red line is the real system throughput, and the dots are the throughputs evaluated in 5 different replications from the models generated with our approach. And we can see that if we generate the models with a smaller dimension, we have to give up some performance, but the average error remains within 5%. So we think that this approach is very promising, and we might develop further towards better results. We have also validated the approach with a real line. We have received a log from a manufacturer which produces electrical motors. The log is a portion of a real line. The log is a 5,000 events log, and we can generate the model from the log. In the generated model, we can also spot that certain activities, in this case the 40 and 50, they are actually composed by 2 different steps. Those steps are manufacturing activities, which are basically related to similar operations, and those operations are very close in time. So the consequence is that the tuning will aggregate those activities into clusters, thus representing again the layout of the real line. So we think that this is very promising because we can represent the real line. And all this has also promising computation times, because all these operations in this slide were completed within 30 seconds. So the approach, however, has still limitations. For example, we have used an hypothesis, and we have assumed to have only a single part IDs, which is not representative of some systems, because, for example, in assembly systems, we might have multiple IDs referring to the same part. Then we also have limited information in the log, and this might result in less descriptive models. And for example, we did not use information related to the resources, for example, the operators. So in the future, we need to further develop this work. We need to design smarter inheritance rules and also improve the local search algorithms. And this is necessary, especially if we want to investigate systems with very large logs, in which we might have a lot of nodes, and so we might need the smarter reduction algorithms. So thank you very much for your attention. I am glad I had the opportunity to present my work in this conference, and I hope to meet you all in person, perhaps in the next edition of the Winter Simulation Conference. So thank you very much again, and have a nice day.